Hello, welcome to lesson 17 on the exponential random variable. This models the time between events in a Poisson process. It's a continuous random variable. The density function is given by lambda e to the minus lambda x for x greater than or equal to 0. 0 otherwise. Lambda greater than 0 is the parameter. We will see that it turns out that 1 over lambda is the mean of this random variable. First thing we're going to do is check that it does meet the conditions of a probability density function PDF. That means that it's greater than or equal to 0, and the integral over its entire domain is equal to 1. So since lambda is positive, this expression lambda e to the minus lambda x will be positive. We got to do the integration on the non-zero portion here and show that's 1. We're going to do u substitution here. U is the exponent negative lambda x. Du is negative lambda dx. Negative du is lambda dx. So the new integral here, we get e to the negative lambda x becomes e to the u, and then the negative du is lambda dx. We're changing limits here from x to u. If x is 0, u stays 0. If x is infinity, u becomes minus infinity. Now, the minus sign on the du we could factor out. Negating an integral reverses the limit, so those flip. Antiderivative of e to the u is itself, and then we have to do the limit for the negative infinity. In proper integral situation, we end up with e to the 0 minus e to the b. E to the 0 is 1, e to the minus infinity goes to 0, so the whole thing does equal 1. And so we do have a PDF here. All right, little generalization here. If you're trying to find the probability that x is greater than a fixed number c, it's basically a similar setup here with the u substitution. And we're integrating from c to infinity. Now, if x is c, u becomes negative lambda c. If x is going to infinity, as we saw before, u is going to minus infinity. And then the negative here, multiplier, flips the limits. We get the limit as b goes to minus infinity. It's e to the minus lambda c minus e to the b. Again, the e to the b term, e to the negative infinity goes to 0. We're left with e to the minus lambda c. That's the probability that x is greater than c. If we want the opposite, less than or equal to, which is the cumulative distribution function CDF, it's going to be 1 minus that. So just using the traditional x variable here, it's 1 minus e to the negative lambda x. All right, the mean or expected value, we're going to show this is 1 over lambda, integrating x times f of x. So this is going to be integration by parts. U is x, du is dx, dv is negative. Du is lambda e to the negative lambda x dx. The integral v is what we just saw. It's negative e to the negative lambda x. We're going to plug this into the integration by parts formula. uv minus integral v du. X times negative e to the negative lambda x minus integral v du. Negative e to the negative lambda x times dx. Negative signs cancel out on that integral at the end, so we get a plus sign here. We can rewrite e to the minus lambda x as 1 over e to the lambda x. We can rewrite that. Integral of e to the minus lambda x is e to the minus lambda x divided by that constant negative lambda. Again, use the reciprocal property for the negative exponent. And we're going to integrate from 0 to b. So we're going to get b over a negative b over e to the lambda b minus negative 0 over e to the 0. Now, this is L'Hopital's rule here. in this first expression, we have infinity over infinity. You do L'Hopital's rule, and you will end up with a constant on top. Derivative of b is just 1, whereas the bottom is going to stay exponential and go to infinity. So this is L'Hopital's rule here. So the format we have here is infinity over infinity. So you have to do L'Hopital's rule on that. It does come out to be 0. The second limit expression there, b is going to infinity. This is 1 over infinity, so this goes to 0 as well. And in the last term there, e to the 0 is 1, so we're left with that lambda in the denominator. The negative signs cancel out, and we end up with 1 over lambda for the expected value. To get the variance, we're going to start out with e of x squared. Now, this is going to require integration by parts twice. So the tabular method works a little better here. We're going to get x squared, and then for u, derivative is 2x, 0. Then the dv expression, integrating. Again, every time we integrate, we divide by negative lambda. So it cancels out the first time with the lambda. Second time through, we get a lambda in the denominator, and then a lambda squared. The signs alternate because of the subtraction and integration by parts. So piecing those products together, we get x squared times negative e to the negative lambda x minus 2x e to the negative lambda x over lambda plus 2 times negative e to the negative lambda x over lambda squared, integrating from 0 to infinity, writing this in limit definition, and using b. What's going to happen again is we have an infinity over infinity situation here in these first two expressions. So both of these, when you do L'Hopital's rule, these will both go to 0. Again, it's infinity over infinity. L'Hopital's rule on these two in the front. This third piece here, that's a constant over infinity. So that limit is directly 0. In the second part, we have a 0 multiplier in the first two terms. So those are 0. The last term, e to the 0 is 1. We're left with a double negative. We're left with 2 over lambda squared for e of x squared minus the mean squared, which is 1 over lambda squared. And so subtracting that, we get a variance of 1 over lambda squared and a standard deviation of 1 over lambda. All right, let's take a look at an example here. The time and hours required to repair a machine is exponentially distributed random variable with a parameter lambda equals 1/2. So note that that's telling us that the mean is actually 2. The mean is 2. Lambda is 1/2. What's the probability that a repair time exceeds 2 hours? So we want the probability that x is greater than 2. So we could do the integration out, or we could do the shortcut. The shortcut is that if you're doing a greater than situation, the probability is just e to the minus lambda times c. And so what we're getting here is e to the minus lambda was 1/2 and c is 2, cancels out to e to the minus 1, or 1 over e, which is 0.3679. So probability x is greater than 2 is about 0.3679. Again, you can use the shortcut there, or you can do the antiderivative. All right, second part. What's the conditional probability that a repair takes at least 10 hours given that its duration exceeds 9? So conditional probability that x is greater than or equal to 10 given x was greater than 9. So conditional probability, it's the probability of the intersection divided by the probability of the given. So it's the intersection of being greater than or equal to 10 with greater than 9 divided by the given probability greater than 9. The overlap of at least 10 and greater than 9 is greater than or equal to 10. So this is the probability x is greater than or equal to 10 divided by probability x is greater than 9. So the 1/2s cancel out here. We can use the shortcut formula. It's going to be e to the minus lambda c. So it's e to the minus lambda, which is a half, times 10. Downstairs, it's e to the minus a half times 9. Subtracting those exponents here, negative 10 over 2 minus plus 9 over 2 is e to the negative a half, which is about 0.6065. Now, notice that this expression here, e to the minus a half, that's actually the same thing as the probability that x is greater than 1, negative a half times 1. So in general, what's happening here is that the conditional probability that x is greater than or equal to 10, given it's greater than 9, it's basically just looking at lasting an additional hour. So it's the same as saying the probability that x is greater than 1. So this property is called memoryless, meaning that everything basically resets. The probability of lasting an additional hour, more than an additional hour, is the same as being greater than 1. So you have this memoryless property. The probability that x is greater than a plus b, given that it greater than a, is the same as starting from scratch and being greater than that difference b. So the probability of lasting an additional b hours is the same as starting from scratch and lasting at least b hours. So you can just do that difference there. Greater than or equal to 10 given greater than 9 is the same as probability greater than 1. So that's the memoryless property. All right, number 2, the number of days that elapse between the beginning of the calendar year and the moment a high-risk driver is involved in an accident is exponentially distributed. They expect 30% of high-risk drivers will have an accident in the first 50 days. What portion is expected to be involved in an accident during the first 80 days? So they don't tell us lambda or the mean here, but they tell us that 30% have an accident in the first 50 days. So the probability that x is less than or equal to 50 is going to be 0.30, and we're going to figure out from here what lambda is. So using the CDF formula, it's 1 minus e to the negative lambda x. That's equal to 0.30 when x is 50, and we're going to solve for lambda here. So this exponential expression has to be 0.70. 1 minus 30, 1 minus 0.30 is 0.70 is e to the negative 50 lambda. Take the log of both sides to cancel out the e, divide by negative 50. Lambda is log 0.7 over negative 50. So lambda is about 0.0071. Remember that the mean is actually 1 over lambda, but we plug this into the function here, and we wanted to get the probability that it's within the first 80 days. Plugging in the lambda and the 80 into the CDF, it's 1 minus e to the negative 0.0071 times 80, which is 0.4333. So answering the question there, what portion of high-risk drivers is expected to be involved in an accident during the first 80 days? And it's about 43%. Okay, third problem up. The time to failure of a component in an electronic device has an exponential distribution with a median of 4 hours. Calculate the probability that the component will work without failing for at least 5 hours. So be careful here. The word is median. Median and mean are not always the same thing. In a normal distribution, they're the same, but not here necessarily. So the median is the value that splits the data in half. So you have half the probability to the left and half to the right. So 4 is the median. So this is 4. And on either side of the median, we have 50% probability. And so we're going to use that fact to figure out what the mean is. So we could use either one. We could integrate from 0 to 4 and we'd get a half, or we could integrate from 4 to infinity and get a half. Actually, the 4 to infinity part is a little bit cleaner. That integral becomes e to the minus 4 lambda. And so apply the log to cancel out the e, and then divide by -4, and we get log of 0.5 divided by -4 is 0.1733. Now remember, that's the reciprocal of the mean. The mean would be 1 over that, but the lambda is what we need for the calculation. And then the problem asked the probability will work for at least 5 hours. So we're integrating from 5 to infinity this expression with the lambda plugged in. And then again, we can use the shortcut. It's e to the minus lambda times that constant. So exponent's -5 times 0.1733. So e to that power is about 0.4204. So it's about a 42% chance of lasting for at least 5 hours. All right, this concludes lesson 17. As always, please don't hesitate to email or ask questions in the discussion board.